In science, we always report our answers to a certain number of significant figures. Now, a significant figure or significant figures is all about how detailed our measurements are, because in science, we're taking real-world measurements. In fact, another term for significant figures could be measurable figures. Now, to help demonstrate that, I just want to do a simple little lab activity here on density to try to see what a measurable or a significant figure might be in application. Now, I could do density, which is mass divided by volume. We're going to do grams using a triple beam balance divided by volume and milliliters using a graduated cylinder, 100 milliliter graduated cylinder over here. We could do that over just a nice, simple rectangular prism object, right? We could stick it on the triple beam balance, we could get its mass, then we could do its volume, length, width, height, and come out with dividing those two, our density. But that seems a little boring to me today. Instead, I prefer to get the density of a BB here. So I have a group of BBs. This means we need to get its mass, taking a real-life measurement, and then get its volume using water displacement method. Now, I've already massed out a container for my BBs here. It's massed out at 111.20 grams, all the way down to 2 decimal places there, because that's what my triple beam balance gives me, which gives me 5 measurable figures, 111.20. So let's actually get the mass of these BBs. Put them in the container. Let's bring all this back to 0 and begin sliding my 100 spot over. 300. 400 seems too heavy. Let's come back. 10, 20, 30. 40 seems too heavy, so let's go back to my 30 spot there and then use my adjustment slider. Come down here, get directly on it where we can see exactly what's happening here. Okay, approximately right there. That now reads 236.85 grams, 236.85 grams. So whenever we subtract the two, the mass, we need to subtract out the mass of my container from that 236.85. We actually come out with a mass of 125.65 grams. That would be my mass of BBs. And so that's going to go in the numerator there. Once again, that gives me 5 measurable figures, 125.65. I know it to 5 figures. I don't know any more beyond that because my triple beam balance doesn't give me any more details. I'm measuring all the way down to half the smallest tick. So let's now look at the volume. So let's take our graduated cylinder here it currently has 50 milliliters of water. Let's pour in our BBs. All right, letting the bubbles settle and then measuring from the bottom of the meniscus. That looks like to me 66.5 milliliters. So I started at 50, I went up to 66.5. That would be 16.5 milliliters for the volume of my BBs. Now that is reported down to 3 measurable figures, or with 3 measurable figures. I'm once again measuring to half the smallest tick, but each tick mark on my 100 milliliter graduated cylinder is only worth 1. So this is going to give me 3 measurable figures. My triple beam balance gave me 5. My graduated cylinder, I could only read 3 figures off of it. So whenever I actually do the math and I do density equals mass divided by volume, that's going to be a density of 125.65 divided by 16.5. That's going to give me, if you just type that into a calculator, 7.6151515151515. You get the point. Grams per milliliter, or 7.615 repeating grams per milliliter. Now that actually has an infinite number of decimal numbers after it, right? It just keeps on going and repeating. That claims that we know this density down to an infinite precision, as detailed as you want to go, but that's just not true. Our triple beam balance, we can only go to 5 measurable figures, and our graduated cylinder to 3 measurable figures. So how can we know our answer to an infinite precision? Well, we can't. That's just a mathematically created number there. We need to round it to try to give an idea of how much precision we actually had in our measurements. Round to the least number of significant figures is the point. Now, my triple beam balance gave me 5. My graduated cylinder gave me 3, so because of the multiplication addition rule for significant figures, I need to round my answer now to the least number of significant figures, which would be what my graduated cylinder gave me, 3 significant figures. So I'll take that 7.615 repeating and round that to 7.62 grams per milliliter, so now it has 3 measurable figures in it.
Now that we've looked at why we need significant figures, aka measurable figures here, let's look at actually how to just identify how many significant figures there are in a number, just in a purely mathematical standpoint. We need 4 rules here, and the first one actually takes care of the vast majority of numbers you will ever encounter. In fact, it takes care of 1 through 9, so 9/10 of them. 1 through 9 are all significant, meaning that 19.32 grams, 19.32 grams, all those are 1 through 9. There are 4 significant figures there. Now we get into all the exceptions, and whenever we're teaching significant figures, we spend time with the zeros because they are the exceptions, even though the vast majority of the time you probably won't even have many zeros to deal with. Now, rule number 2, sandwich zeros. That's zeros that are between significant digits, kind of like this or like this. They're stuck between 2 numbers there, 1 through 9. Those are significant, meaning this one has 4, 1, 2, sandwich 0 counts. So that's 3, 4, and then this one also has 4. 1, sandwich 0, so that's 2, 3, and then 4 there as well. The next rule, leading zeros. That's zeros that are actually in front of numbers 1 through 9. They are never ever significant. For example, in this one here, these 2 zeros are out in front. There isn't another number over here that would sandwich it. It doesn't matter where the decimal is for how many measurable spots. In fact, the only reason these are here isn't to indicate that we were able to measure that. They're there to hold the place so the number doesn't actually change. So these are not significant even though you can't just erase them off. We have, don't count, 1, 2, 2 significant figures. Lastly, trailing zeros. These are zeros that are behind numbers 1 through 9. They are only significant if there is a decimal. So whenever you see trailing zeros, ones at the end, like all of these, a little alarm bell should go off in your head that says check for a decimal, check for a decimal. So here, 1, 9, those are significant in this 190 grams. 0. This 0 is at the end. It's trailing. Check for a decimal. There is no decimal anywhere in here, so there are only 2 significant figures because that trailing 0 does not count. On the other hand, this next one, 190 with a decimal, trying to indicate that we do know this ones place. This is saying we don't know anything about the ones place. We didn't measure it. It wasn't, our measurement tool wasn't detailed enough. This is actually pointing out this wasn't 191. This is exactly 190 here. So we do know the ones place. So if we look at significant figures, yes, 1, yes, 2. Trailing 0, check for a decimal. There it is. It's significant. That must be 3. This next one, 190.0. This decimal here is trying to indicate now we know all the way down to the 10th place. So there's 1, 2, 3, 4 significant figures there because they are trailing, and there is a decimal somewhere in the number. It doesn't matter where the decimal is. Lastly, 0.01900 here, grams. Now, these are leading. Leading do not count, so they're not going to count here. I got 1, 2, and there are trailing zeros. They're at the end of the number. Check for a decimal. Doesn't matter where it's at. There is a decimal in this number, so there must be 1, 2, 3, 4 significant figures here, meaning that those zeros back there, they're not holding a place. I'm trying to indicate that my measurement tool actually could have measured down to it. Now that we know how to identify the number of significant figures or measurable numbers, measurable figures, let's look at actually using them mathematically. There are two rules that you need to know: the addition, subtraction rule, multiplication, division. Now, addition and subtraction is all about the number of places after the decimal. Basically, you should never have more numbers after the decimal than the least, because you are only as strong as your weakest link. So take this example over here. Maybe we'll blow that up for us here. I have a water displacement going on. I started out at 50.0 milliliters, indicating I can measure down to the tenths place, and then I put the key in and it went up to 52.4. So whenever I subtract these two, this is going to turn out to be 2.4 milliliters. And the key here is that both of these go down to the tenths place. From that, I need to make sure my measurement goes down to the tenths place as well. The only time this could get really weird is if you use two different measurements, two different graduated cylinders to make your measurement. If you use two different graduated cylinders, let's say this one actually was more detailed. Maybe this one went to, instead of 52.4, this went to 52.43. Now, if that's the case, if it went down to 52.43, then whenever I subtract the two, I actually come out with 2.43 milliliters. But that has too many details in it. We are only as strong as our weakest link. We took one measurement and it only went down to the tenths place. We took another measurement, it went down to the hundredths place. We're only as strong as our weakest link, which was down to the tenths place. So I need to round this 2.43 to the tenths place. That 3 does not push the 4 up. So this would again become 2.4 milliliters. Now, in the multiplication division rule, it's about the number of significant figures as opposed to, in the addition subtraction, number of places after the decimal. So it's just how many significant figures do you have in multiplication division. And once again, you're only as strong as your weakest link. So let's look at a little example calculating velocity. Velocity is displacement. If you haven't had physics or IB physics, that S might be a little weird, but that stands for displacement, or in essence, how far you go, divided by time. And then I have some measurements that I took about this car. We timed it out and took 32 seconds to cover, measured a distance or displacement, 395 meters. Now, whenever I actually do the math of this, velocity displacement divided by time, I come out with 12.34375. This is giving a really insane precision whenever it comes to velocity, and it's more precision than the measurement tools that I had. Remember, you're only as strong as your weakest link. In a multiplication division, it's about the number of significant figures. So in the time, I had 2. In the displacement, I had 3 significant figures. So my weakest link, the time, only has 2 significant figures. So I need to round 12.34375 to 2 significant figures. The 2 most important, the 1 and the 2, the bigger ones. The ones further to the left are obviously more important. I want to keep the 12, not these little numbers over here. So the 12 would be the most important. Look at the next significant figure, 1, 2, keep those. 3, does the 3 push the 2 up? No. So this is a velocity of 12 meters per second.